another topic we call power transformations. Now, why do we need this? Why do we need power transformation? Okay, let me tell you this. What we do in statistics, it's like a story, a stories that goes on and on and on. Okay, so why do we need power transformation? We need power transformation whenever there's a problem. Okay, how am I going to know? How am I going to know there's a problem? Of course, when you do regression diagnostics, you remember the other time we did regression diagnostics. In regression diagnostics, or where we make use of residual plots, the QK plots and the like, we'll be able to know which of the assumption is violated. Okay, and of course, not only assumptions, what about if there's outlier or if there's a high leverage? Of course, how do we fix a problem? So today's topic is actually is an okay, when there's a problem with a model, how are we going to fix it? And that's why we call it power transformation. Does that make sense? But you know what? If there's no violation, if there's no problem, we don't need today's topic. Does that make sense? If everything is okay, we don't need today's topic. Okay. Okay. Now we're going to consider variable transformation, like I said. Okay, where we use a function of the random variable to replace variables. Let me tell you this. In every statistical model, okay, in every statistical model, we normally have, variables as part of the model. Let me tell you this. Whenever there's a violation, then it means our variables in the model are not presented appropriately, and therefore need to be transformed or need to be replaced. And that's why you see, use a function of the variables to replace the variables. Okay. Now, I need you to take a look at this. I want to talk about different kind of transformation right now. Number one is what we call linear transformation. Okay, linear transformation, maybe for instance, I got the variable W, okay, specify, and there was a problem. Then I decided to say, okay, let me multiply by a constant. When you multiply a variable by a constant, then that's a linear transformation. Or you are adding, if you take a look at this guy here, what am I doing here? I'm no longer using W because W is problematic. And what I'm doing, I'm only adding 1 to that. Or I'm subtracting, okay? These are examples of a linear transformation. And let me tell you this. This is the most simplest transformation ever. And this may not work. All right, they may not work. Okay, because of that, we're going to consider another type of transformation. Oh my God. Another type of transformation is what we call power. Take a look at this. Initially, the W that I specified in my model was problematic, and I decided to take it to square that. At times, when you construct a scatter plot, right? It doesn't look a straight line. It may look like a curve. Okay, that may require quadratic, right? Then if you actually want to, remodify the model, you're actually going to say, okay, going to square your variable. And at times that may not also work. We can also do to power 3. Okay, we can even do to power half. Which means if I have a W raised to power something, that needs to be determined. Okay, what is raised to power needs to be determined. Okay, and another time it could be other transformation that may work. It could be that, okay, my W is problematic. I need to take a sign of W. And somebody, okay, I need to take a cos of W. Or I need to take a tan of that. I need to consider the trigonometric for W. Okay, and let me also tell you this. At times, it may be 2 variables that may be problematic in a model, W1, W2. Like tomorrow now, we're going to start multiple linear regression, where we're going to have more than one explanatory variable. If I have more than one explanatory variable in my model, okay, and the module is problematic. Okay, maybe the way I actually put W1 and W2 in the model is not in an appropriate statistical form. Maybe what I need to do is maybe trying to look at their ratio. Okay, W1 divided by W2, and so on like that. Okay, so these are, like I said, these are the kind of transformation that we have. Okay, okay, so but we don't know the one that is going to work unless we try. That's why I'm going to walk you through some. Now, please pay attention right now. Oh my God, I needed to pay attention to this. In a power transformation, we don't know what the lambda is going to be. When lambda equal to 1, what happened? No problem. When lambda equal to 1, it means our W is in a very good statistical standing. Okay, so what do we need to do? When there's a problem, then it means we need to determine the values of lambda. That needs to be determined optimally. Okay, and you know what? We're going to use that kind of transformation when lambda is not equal to 0. Okay, now, but when lambda equal to 0, we use another transformation, which we call a logarithmic transformation. At times, we could log our variable when the variable is problematic. Okay, in that situation, lambda equal to 0. Is there any question about this transformation? Is there any question? Okay, now I'm going to show you the graphical. Oh my God. I'm going to show you something right now. Okay, and I'm going to, let me first indicate all of that. Okay, I just wanted to see a scatter plot when lambda equal to 1. Can somebody see when lambda equal to 1? No problem. That's a straight line. Do you see that black line? Do you see this guy, right? Do you see that guy? There's no problem at all. How am I going to know this? And that's why you need to start by first. When you are trying to characterize relationship between two variables, you need to first generate a scatter plot, which is like plotting response against the explanatory variable that you actually gonna see there. When lambda equal to 1, when you have a straight line, that is telling you you don't need transformation here. Okay, now I needed to see when lambda equal to 2. You see, when lambda equal to -1, when lambda equal to 0, you see the green line. When lambda equal to, so I needed to be able to take a look at what I have right now. You're actually going to see that, this is the kinds of, these are the possible shape you're actually going to have, okay, when you plot. If you take a look at what I'm plotting here, I'm plotting the transform W against W. Okay, the W that has been transformed against the original W. Okay, now the W that has been transformed, I'm trying to say when lambda equal to that, and that is the shape you actually going to see. Now, I have a question here. Identify the power for each line in the graph on the right. Select the power for the following. Of course, that's what you can see. Okay, now, another question now asks, why use log transformation for lambda equal to 0? I think I think I'm going to tell you that for lambda equal to 0, why use log transformation? Because when lambda equal to 0, okay, when W raised to power 0 is what? 1, right? Okay, and you know that when that equal to 1, what is the log of something that can give you 1? What is log 0? Or something. What is ln 1? Natural log of 1. That would be 0. You see that? Okay. I'm still going to talk about that as time goes on. But this is just to show you, okay, different kind of transformation that actually work. Okay. That's to show you that. Okay, so why do we transform our variables? I said just because a variable is given in the data set doesn't mean it is appropriate. I told you. Let me tell you this. We normally get things wrong right from the specification of a model when a model is wrongly specified. Okay, at the beginning, because when you are using statistical framework, okay, using statistical framework, we normally start by specifying a model using what I call the principle of subjectivism. Okay, when I say subjectivism, my ideology may be different from your ideology. You could see a different statistician specify a different model for the same goal. Okay, so now, but we got to make sure that our model is specified correctly. And the moment that we specify a model does not mean the model is correct. That's what we're trying to talk about. Now, another thing is, and I'm going to give you an example of this. When the study of a country economy development on child mortality rates, what are the variables that I want to use? Child mortality rate, the GDP and population. Now the question is, how am I going to specify this in my model? I'm actually want to study a country economy development, okay, on child mortality rate. Now I need you to take a look at this now. If in my model, if I consider child mortality rate on GDP only, there are different kind of GDP. Am I talking about GDP per capita? Look at what am I doing here? We're trying to say when you are specifying do GDP divided by population. You remember when I was showing you the other time I said W1 divided by W2, right? Okay, so when you take a look at that, okay, what you see here, if I specify it that way, then my model is adequately specified, okay? Because, in some, you're only going to see a child mortality rate. They're going to consider if they're going to say child mortality rate equal to GDP plus population, where they're going to look at the effect of GDP on its own, population on its own. No, that's going to be wrong. But what we're trying to say, why can't you combine GDP and the population before you put it in a model by doing the ratio of that? That is actually going to make that variable to be uniquely specified. Okay, when variable is uniquely specified in a model, then it is in a good statistical standing. Go ahead. Oh, you mean if I use a different way of... No, even if it's one, we can transform one, because one may not just be a GD. Let's say, for instance, the other time we're talking about we've read my professor data. We talk about using professors' clarity to determine quality. Okay, if we plot and realize that it's not a straight line, we could be thinking to redefine quality, maybe quality raised to power 2 or quality raised to power half and so on like that. But we may not know the transformation that work unless we try possibility. Does that make sense? So the way we transform multiple variable, we can also transform a single variable. The most important thing is for the variable to be in a very good statistical standing. Okay, now another major reason why we transform our variable. Let me tell you something. I told you there are two reasons. The first reason is to put the variable in a unique form. Another one is to fix assumptions violations. This is a major one. When assumptions are violated in a linear regression, how do we fix that? Okay. Now the question is, does the linear transformation help? The linear transformation help me not. Linear transformation may not help all the time, because I showed you the other time. Linear transformation is like adding constant or multiplying constant. That may not actually help. Now, I want you to pay attention now. I want to cite an example. We want to model salary from years of experience for professional workers. We're now looking at the variables to use. Okay. What is problematic to a model is when you want to work on something, but you did not specify your model accurately. Okay. Now this is what I want to do. Using years of experience of workers, I want to determine something. Take a look at this. I want to predict salary using experience of workers. If I use salary against experience, even if there is no violation, even if there is no violation, this is not in statistical standing. I told you there are two reasons why we transform. Number one, to put variable in appropriate statistical form, right? Number two is when there's a violation. But I want to show you something. Instead of us to use just experience, if we use work history index, okay? The work history index here, take a look at this. Instead of using experience, and I want to use a linear transformation where the work history index is experience minus 1 divided by 40. Can somebody tell me, why do I divide by 40? Can somebody tell me for extra credit? Whether in person or online, why do I divide by 40? I'm talking about I want to compute the work history index, and it is experience minus 1 divided by 40. Where is the 40 coming from? 40 is the numbers of hours they work per week. 40 hours per week. Does that make sense? That's what it means. 40 hours per week. What I'm doing there is just like experience minus 1 divided by 40. That's a linear transformation, right? Okay. But if we now want to argue it, that instead of you, even though there's no violation, instead of you to use experience in this model, okay, if you use work history index instead, that doesn't change the information. Let's see. Oh my God. Look at that. Is there any change in shape? But why are we not using this? This doesn't sound okay in economics. Just trying to look at the experience. Okay, it is better to specify work history index. And the work history index is a linear transformation of experience. Does that make sense? So the linear transformation doesn't change the shape. But do you know what changed the shape? What's changed the shape is a power transformation. There's a difference between, we have a linear transformation. The essence of the linear transformation is to put the variable in a unique statistical position. Does that make sense? You want to ask a question? Why do we do what? Oh, why do I subtract one? We've looked at the mathematical, uh, of it. Like, okay, what we're going to do. That is a formula provided by economists to calculate the work history index. Does that make sense? That is a formula. But to us in statistics, that is a linear transformation. Why linear transformation? Because it doesn't change the shape. When you use the original variable and the transform variable, does that make sense right now? The shape is the same. If you take a look at this guy here, when I use experience and when I use work history index. Okay, now I want to move right now. Okay, now, oh my God, I asked this question in the exam. Okay, I asked this question in the exam. Now, predicting brain weight based on the body weight of mammals. You know what? When we generate a scalar plot between the brain weight and body weight, we see something here. Do you see that point? Those 2 points? Asian elephant and African elephant, they are actually not consistent with others. Okay, and what does that indicate? That means you should suspect a violation, right? Okay, now what are we going to do in this situation? Okay, now when you have something like this, Okay, initially this is a model, right? That model cannot be trusted because of the fact that if you take a look at this, we got some outlying points that need to be investigated. Does that make sense? Now, let us assume that it's going to be problematic. How can we fix it? Somebody can argue it out. Oh, maybe we should remove the two. No, you can't remove them. They are elephants. Then you need to transform your model. Does that make sense? You need to transform your model instead of removing them. Now, I'm going to show you, and that was why it has this question here. Okay, does this model fit the data well? It may not, because of the fact that we can see some outlying observations. Okay, now take a look at this. Somebody will argue, let's remove them. But I can tell you, when you remove them, it doesn't make a difference. When you remove them, look at what you have. It doesn't really make a difference removing them. Okay, then what are we going to do? Now take a look at this. When you generate a residual plot for them, you can see, you're still seeing that 19. Can you see that? Okay, if that's a residual plot for that, and if you generate a normal QQ plot, is that a normal? No, a normal QQ plot for data set to follow normal, what should happen? That should be a diagonal straight line. But this is an horizontal. What have you seen here? The normal QQ plot is indicating when you fit a linear regression model for this data, there's going to be a violation of normality as displayed by a normal QQ plot. And there's also going to be a violations of linear, the linearity, because an outlier, if you take a look at that, there's a violation. Take a look at all of that. Now, what are we going to do? Please pay attention. We now want to consider power transformation. We want to see, we know there's a problem now. And we don't want to remove the two elephants, right? How are we going to model that in such a way that the model will ignore the potential threats posed by the two elephants? Then we're going to consider transformation. Now, we want to consider 4 different transformations right now, but let me tell you this. You have to think about what kind of transformation I'm going to use. There's so many of them, but which one am I going to try? Oh, because we're talking about weight, there's possibility that is going to be skewed to the right. You know what I call skew to the right? Then when something is skewed to the right, when you have a positive skewness, then you need a transformation that will bring it to the center. It's to the right. What are you going to do? To the center, you want to bring it to the center? It means the data is too heavy, right? The data is too high. Then you need to look for a transformation that compress, like log, square root. Oh my God. Here, you can't consider a transformation of S square. No, you're complicating the issue because this is skewed to the right. You want to bring it to the center. Now, take a look at this. The first one that I consider reciprocal. Okay, 1 over brain weight. Instead of me to plot a brain weight against a body weight, I do 1 divided. When I do 1 over that, it's going to be reduced, right? I plot that. It doesn't solve the problem. What did I do again? I do the log and log. What did I log the y and I log s. Then I actually plot them. Then I do the cube root and I do the square root. Can somebody tell me which one give us a straight line? Which of the transformation give us a straight line? It is a log. Does that make sense? So I may not know the transformation that's going to work unless I try. But even though I get so many transformations to choose from, but I need to choose about the units of the variable I'm talking about weight. Asian elephant and African elephant, we actually make the distribution to be skewed to the right. Then I needed a transformation that will compress. What you do in high school, that you do the log, you do the square, you don't really understand, you don't know the meaning until you get to the college. Oh, taking the log means I'm compressing, or square root, I'm compressing, or reciprocal. Okay, now let me tell you this. When I plot my variables and it doesn't give a straight line, if I actually transform the model, I'm actually looking for the transformation that will bring us back to straight line. And which one? The one that brought us back to straight line is this guy. And therefore, the transformation that work here is the log transformation. We log the response variable. We also log the explanatory variable. Okay. And that was why I think I said, why do I use the same? Why do I use the same transformation? And let me tell you this, at times we could log y and not log s. We could have a straight line. But why do I need to log in the both case? Because the brain weight and the body weight is weight and weight. They have the same unit. Is if the body weight is affected, then the brain weight is also going to be affected in this case. But I don't know the transformation that work. I can try possibility, like I said. Okay. Now look at what I said. There is no requirement that x and y have to use the same transformation. Okay, no requirement. Accidentally, in this case, the log and log actually work. Okay, now, but it is reasonable here because both variables are weights. Okay, now go ahead. Can you say that again? What is the point? Oh, the verification, like the other ways of verifying power transformation that work. Is that what you mean? Yeah. Actually, before I'm going to come up with this, I have to first of all consider like what kind of skewness. I think the most important thing because there's so many transformation to choose from. Okay, there's so many of them, sign, whatever. But our four of us need to put the skewness. You know what they call skewness? I've heard about skewness. Oh, okay. Now, if your data has a positive skewness, then the transformation that will work is the one that will compress. And that was why I was looking at reciprocal. I was looking like the log of that. But you just have to try all of this before you'll be able to know the one that work. But you need to have advanced knowledge of the skewness so that in order not to waste time to try so many, there's so many of them. I can't even count them. Have I answered your question? Okay. Now, oh, okay. Advertisement time. Now, I want you to look at something now. For the residual plot, when I did not transform, this is the way residual plot look like. You know, I told you this residual plot has a problem, right? There's a violation of linearity, violation of constant variance for this. Okay, and that was when I did not transform. I used brain weight on the body weight. But after transforming, let's see the residual plot. Oh my God, we're gonna start celebrating now. How am I going to know whether an intervention work? How am I going to know? We should have a threshold. We should have like a yardstick, something to investigate, to evaluate whether a particular transformation work or a particular intervention work. In this case now, what we're going to do, you know, how do we know there's a problem in the first place? We use diagnostic plot, right? Now, if we have transformed and there have been intervention, how am I going to know whether we have solved the problem? We're still going to use diagnostic plots. But right now, look at that. Look at the way it was. And look at this. It's work for this. Do you see that? Log on log, which means if I want to do my regression model, four of us log the variable, the two variable before I'm actually going to get all of that. Does that make sense? Now, what is the code in R? This is the code. Please wash. That is the code. You see what I did? Mode 2. Because mode 1 is when I just do this. But mode 2 is lm log of that on log of that. And the name of my data is mama. If I want to have access to the plot, I'm going to say plot that 1 is going to give us this. Plot that 2 is going to give us that. Does that make sense? That is the code in R. Okay. Now, Take a look at another one. Okay, if you take a look at the code here, 1 is for residual plots. 2 is for normal QQ plots. Now, take a look at this now. I'm going to show you a normal QQ plot now. Okay. Now I'm going to show you. Let me show you the code. Do you see the code? What is different? MOD, 2. Just going to give you this. Oh, before there was a violations of normality as displayed by QQ plot, but after transformation, what happened? No violation anymore. That is a way to tell. Does that make sense? Okay, now, why does log transformation work for this study? We really want to know. Why, when we use logarithm of this and logarithm of that, and that work, why does it work? Do you know why it work? It worked before. Initially, the relationship was not a straight line. The relationship was multiplicative. Does that make sense? Now, you know what I want to do now? We now want to trace the origin of the model back. Take a look at this. Please take notes. Okay? Initially, this is the model. This is a multiplicative model. Brain weight equal alpha times body weight raised to power b. Anytime you say this, this is a multiplicative model. But you know what? Whenever we have a multiplicative model, we can linearize a multiplicative model. What are we going to do? We're going to take a log. Let's take a log of this. Take a look at this. Take a natural log. Okay? When I take the log of that and the log of that, I'm going to get all of that mathematically. Then I'm going to have, you see that? I'm going to have log of this, log of alpha, plus, log of a product is you're going to be sum of the log. And when you take a look at this, finally, you're going to arrive at this. This is the model we use eventually. But the origin of this model, this model here is linearized now after taking log. But what was the origin? The model this is the origin of the model. It was multiplicative initially. This attempt is to linearize a multiplicative model in mathematics. If I want to linearize a multiplicative model, I can take a log of both sides. That will enable me to use a linear technique. Take a look at that. That's why it works. Okay. But what if you don't know what the model is supposed to be like? Then try possibility. Does that make sense? That's how you try possibility. But if you don't want to waste your time, focus on the skewness. Does that make sense? Because there are going to be so many. Okay. And that was what I said. In the future lecture, general process of variable transformation will be discussed. Okay. Now, a very quick to what we've done. A power transformation. I introduce it to that. Right? Then here, where power transformation is very useful in what? 1, to obtain linearity, to stabilize unequal variance, to obtain normality, and to even to get rid of unusual observation. And not only this, it also helps to make the variable in our model to be correctly specified. Does that make sense? So take a look at that. But let me tell you this. Oh my God, but not guaranteed to fix problems. And that's why that's why story continues. Okay, no guarantee. Okay, also, what if your variable values are negative? Can we log negative? We have to think of something else. And that is why in the future, we're going to talk about boss cost transformation. There's a lot of advanced transformation in this course. Does that make sense? Statistics is like a story, right? A story that goes on and on and on. Okay, now I want to use this opportunity to start this topic is dummy variable. We've done, it's still under, do you know what I just want to achieve this within 10 to 15 minutes. Dummy variable is when we use dummy variable when the explanatory variable is categorical. You are regressing. We've been dealing with continuous, right? Like body weight, brain weight on body weight. That's continuous. What of in a situation where my explanatory variable is categorical? Categorical in the sense that it is either yes or no. Okay, then we're talking about dummy variable in that situation. Now, in the end, you'll be able to understand what is dummy variable and how do we fit regression model with dummy variable, okay, as a predictor variable. The predictor variable here is dummy. And what do we mean by dummy? Okay, take a look at this. By dummy, okay, a variable that can take on different values, 0 or 1. For instance, I want to look at the effect of gender on salary. Okay, that's going to be a dummy variable regression because the predictor variable is categorized. Does that make sense? Okay, and that's why, it doesn't matter. I put 0 here, 1, it could be 1 or 0. That's no problem. Does that make sense? So 0 and 1 are used to represent different level of a categorical, and 1 is not necessarily better than 0 or vice versa. It's just nomenclature for labeling. Does that make sense? Okay. Now, but this is a situation where we got 2 categories. Okay. We could have more than 2, but I want to focus on that. Now, take a look at this. What is the relationship between wage and marital status in 1985? Oh, wage is the response. Marital status is the explanatory variable, but marital status is categorical. It's either you are married or not married, right? That's categorical, right? Now we collected in 1985 current survey, X represent status, which is married or single. X there is categorical, but Y wage, of course. Now we collected this data set. There's a lot of them. This is just the first 6 in the data. Okay, there's a lot of them. Go ahead. Oh, you mean before it's categorical, we need to transform? Is that what you mean? Yeah, but you know what? How do we do that automatically for us? I'm still coming back to that. You know what is going to happen? How do we just take one of the category to be 0? Like you don't necessarily going to do that. And that's why we are adopting software. But if you want to run it manually, if you want to do it manually, we got to decide on the one we're going to label as 0, the one we're going to label as 1. That's a good question. Okay, but there's something that we need to do. Even though we want to look at the relationship, we need to first generate a box plot. Has anybody seen this guy box plot, right? Anybody see that? We generated a box plot for married and single. Okay, of course, this box plot is giving us certain information, right? The average here is for married workers is more than that of single, based on what we're seeing here. Does that make sense? But this is what we're going to do. We're going to run the regression, okay? The just like the same way we normally run regression. Oh my God, this is the code. It's easy. It's what we've done before. The only thing is that we are emphasizing on the explanatory variable that is categorical. Does that make sense? Okay, but I needed to pay attention to the output. Please pay attention. This is critical now. Take a look at this. What is that? Status single, right? You know what arrow is telling me? Arrow is trying to say that he has labeled married to be 0. Whatever that show us in your output is what arrow label as 1. It means arrow label single as 1, but married 0, which means married is nested. It's actually is using that as a reference point. Does that make sense? So please pay attention to the output. Okay, this of you online, you also see that, right? Okay, now let me tell you this. You know this. You know what that guy mean? That is what married got on average. Married is in the intercept. Whatever that you actually label as 0 is what is in the intercept. Does that make sense? Okay. And -1, that is the difference between the salary of married and the single. Who hand less? Single hand less. Because that's the negative. Can you see negative 1.0866? Can you see that? Okay. Now, if I want to write a model out, okay. Oh my God. This is the model. Can you see wage equal 9.40? I'm using this to 2 decimal. To 2 decimal. Does that make sense? Okay. Now, if I want to predict the wage, when status single equal to 0, when you plug in 0 here, then the married workers is getting $9.40. But if you want to predict the wage of a single worker, you're going to plug in 1. When you plug in 1, that will be 9.40 minus 1.09. Then the single worker had less. Does that make sense? Based on the model, now I'm going to show you this right now. If you don't understand, please ask question. Oh my God. Do you know that? Do you know that what we're doing here is the same thing as comparing 2 groups in the t-test that you've done before coming to this class, where you are comparing the salary, the average salary of married and single, which is the difference of means. Have you heard about difference of means? Now, what I'm trying to say, difference of means is the same thing as the slope. Look at that. The mean, this is the mean of a single worker minus the mean of a married worker is the same thing as the slope. Now, when the slope is significant, you know what happened? When the slope, I've told you how to test the significance of the slope using the p-value, right? If you want to take a look at this guy now, what do you see? That is significant, right? The p-value is less than 0.05. Okay, if beta 1 is significant, you know what that means? It means in your t-test, there's a significant difference between what they are getting, which is this. This is what you did. This is what you did before coming to this class. You remember? This is what you do. If you don't want to approach it, using linear regression, using the dummy regression, what am I trying to tell the world right now? Dummy regression model is the same thing as 2 sample t-tests, because you are comparing 2 groups. So this is a formula comparing, this is the hypothesis, what you've done before. The non-hypothesis is trying to say the salary of a married worker is the same as the salary of single workers. The alternative is saying they are not the same. By the time we compute the p-value, okay, we got 0.02009 for the t-test, and 0.020 if you take a look at this guy that you're going to get for the t-test, oh my God, it's also going to be the p-value that you're going to get for the slope. Look at that. They're going to be the same. Therefore, 2 sample t-tests of means is the same thing as dummy regression. When beta 1 is significant in the dummy regression, then it means you're actually going to reject the non-hypothesis that say the two are, the average of what married workers is getting and what single workers is getting is not going to be the same. But let me tell you this. Can I shock you now? I'm going to tell you this. This may not be appropriate. Why? Can somebody tell me why this may not be appropriate? Why we still need to do something more? And that is the reason why we want to start multiple linear regression tomorrow. Because right now, we're looking at the effect of marital status on wage. And we can see that marital status, is significant, right? It's significant because the p-value, but we have not considered some other variables that could also affect wage, like years of education of workers, years of experience of workers, the sector workers belong in the company. We have not considered that. And that is the reason why we are starting tomorrow's topic, multiple linear regression, where we actually, because if you are looking at the, even though this is a primary variable of interest, we are looking at the effects of marital status on wage. If there exists some other potential variable that have effects on the response, if you don't consider them, if you don't include them in your model, this is going to be an exercise in futility. And that accounts for the reason why we need to consider more variables in our model. We don't just put variables in our model, but we need to include variables that actually that we believe may contribute. But how am I going to know? Do you know how I'm going to know the variable? I want to conduct a study and I'm actually looking for variables that have a connection to the response. What am I going to do? I need to review literature. You know what they call literature? Because you are not going to be the only one that have done work on that area before. You need to look at articles. You read articles to be able to know some potential variables that are connected to the response variable. Because if you ignore them, and you only consider few, then your model is going to mislead. We don't want a situation where at the end of the day, we're going to, we spend a lot of time building a model, we spend a lot of money, but at the end of the day, because we did not consider all relevant variables in the model that have connection to the response, and at the end of the day, whatever decision we make, whatever recommendation from the model will not see the light of the day. And that is why it looks as if our models are failing us. Our models are not failing us. We are the one that we are not doing the right thing at times. Is there any question before I go today? My time is up. Okay, those of you online, you're also good, right? Yeah, you have any question? Any question? Okay,
No.
okay, thank you so much. The only condition, Logos, that I'm going to be allowing students to attend lecture online is to be in the lecture, to ask questions, because I have this experience when some students log in, they're going to mute, they're not going to show the video, but they are far away from lecture, they're going to be doing something else. I don't want that, okay? So if you're going to be attending my lecture online, you need to be around, okay? Make sure you all stay safe. I'll have a lovely day. Bye. For now, we're starting another chapter tomorrow. Stay safe, everyone. Yep, you're welcome. Yep.